Welcome back everyone to this series of tutorial problem solving sessions from design. In this video, we'll be solving this simple problem from the static failure theories or simply the theories of failure. So before solving this one, I will be just introducing you or giving you an overview of the theories of failure. In last problem solving videos, we have evaluated we have calculated the principal stresses for the critically loaded point within the element that is subjected to combined loading, and the same evaluation of principal stress will be applied here, and then we will be applying the failure theories for solving. So here in this type of problem which are involving the application of failure theories, the first step will be to evaluate the principal stresses. So here I am explaining these steps to follow for solving such a problem from this failure theory. First, based on the loads given on the member, you need to evaluate the critical, or you need to identify the critically loaded element and the critical the stress values. That means if the member is subjected to the extreme cases, it may be subjected to combined axial force, torque as well as moment based on the type of loading. In some cases one of the any one of these load may be absent. So based on the type of loading, you need to evaluate the critically loaded element or the point, and then you need to represent the state of stress, general state of stress, that is sigma x, normal stress along x and y direction, then the in plane shear stress tau xy component produced because of this loading. Then from these components you need to evaluate the principal stresses. This we have seen while solving the previous problem. So this is the magnitude of principal stresses. So once you are evaluating the principal stresses, then you can apply the failure theories. So we have studied 5 theories of failure. First I will be giving you why we are using theories of failure. See, we are getting the properties of material. Static loading means the load where it is constant with respect to the time, or it is steady with respect to the time. So the actual this property sigma y is obtained from uniaxial tension test, where the type of loading is uniaxial, or it is acting in a single direction, and it is axial load. But the component may be subjected to combined axial bending or twisting moment. So in such cases, you cannot predict the failure based on this property sigma y, which is obtained from uniaxial test. So you need to compare some other parameters with respect to this standard property sigma y. Actually, I have made a video on this one, that is why do we need to formulate the theories of failure. The link for which the same I will be provide in the description. So anyway, that failure theories, because of that reason only we are using, and static failure theories where the load is constant with respect to time. We will be studying or will be analyzing 5 different theories, and it is based on the criteria, which criteria we are comparing with the non-property sigma yield or sigma ultimate. Sigma yield property will be used for the ductile materials, and sigma ultimate will be used for the brittle material. So in maximum principal stress theory, or it is also known as maximum shear stress theory or Rangine's theory, we will be comparing the maximum principal stress with respect to the non-property, or which is obtained from the simple tension test. And for safe working, the maximum principal stress should be lesser than or equal to the property divided by factor of safety. Factor of safety will also be taken into consideration. Otherwise, just simply sigma y. So in limiting case, I can apply the equal sign or condition, where sigma 1 equal to sigma y by FOS. The same equation is given in the data book also, equation 2.8a. You can make use of this one, where the sigma E is actually representing the effective or equivalent property, that is sigma y by Fs, and right hand side only you have to look for, which is sigma 1. And the previous step I have shown you how to obtain the maximum principal stress sigma 1. And in the next theory, it is maximum shear stress theory, and I have shown you the steps. Anyway, finally we only need this expression, which is also given in the data book, which is sigma 1 minus sigma 2 is equal to sigma y by FOS, factor of safety. This equation will be solving in cases where we need to apply the maximum shear stress theory, or it is also known as Gust-Tresca theory. The same equation you can see here. You need to only look for the left extreme value. This sigma AE or equivalent is actually representing the property sigma y by Fs, and right thing is actually based on the load applied, that is sigma 1 minus sigma 2. The simplified expression is this one. So this is the maximum shear stress theory. Similarly, I will be showing you the other 3 theories equations also. Next one is maximum principal strain theory, where we will be using this equation sigma 1 minus mu sigma 2. Earlier it was only sigma 1 minus sigma 2. Here it is sigma 1 minus mu sigma 2 equal to, again the right hand side is same, sigma y by factor of safety, by assuming that it is a ductile material. Otherwise we need to use sigma ultimate, sigma u by FOS. The same equation you can see here also. The left one is this actually sigma y by FOS, and right hand side is sigma 1 minus mu into sigma 2, which is actually this term. Similarly, the other two equations for maximum strain energy theory or Haick's theory, it's given here. Square root of sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 equal to sigma y by FOS. The same thing you can see here. There, where this one, sigma e is this one, and this term is actually shown here. Similarly, last theory is the maximum shear energy theory or discharge energy theory or von Mises theory. It is square root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 equal to sigma by FOS. So these equations are given in the data book. So based on this one, we will be solving a simple problem. So here again I am showing you the data book pages that is containing these required equations on page number 21 and 22. These equations are highlighted here. This is the first theory and this is the next 4 theories of failure. Each name is also shown here. So here we will be first starting with the problem. Here we are having a mild steel shaft whose diameter is unknown, and that diameter we have to evaluate based on each of these failure theories. So diameter is the unknown, and this is subjected to a bending moment at its critical point. So we need to only think about the values at the critical point. There is no need to evaluate the critical sections or critical elements. Only we need to take the values. Bending moment at the critically loaded point is m equal to 3500 Newton meter. It is given in the SI unit. And the other one is, it is subjected to a torque also. So it is a combined loading case where bending moment and torque is acting. Torque value is 2500 Newton meter. So next step, we need to evaluate the principal stresses as I mentioned earlier. For that, based on the previous idea or understanding, we need to we need to find the type of stresses developed because of these applied loads. So because of the bending moment, bending normal stress will be produced, sigma b, and because of this applied torque, torsional shear stress will be produced. And the equations or expression for this one is given in this data book page, or equations 1.1. If it is subjected to bending moment, the equation we will be making use of this one, that is 32 m by pi d cube. So this sigma b will be equal to 32 m divided by pi d cube. And if it is subjected to torque, then torsional shear stress equation, this will be applied, 16t by pi d cube. And I will be marking you the critical element. Critical element will be lying at the outermost top surface, because in earlier videos I have shown that same thing. Torsional shear will be maximum at the extreme point from the center or at along all points of the outer surface. But with respect to bending, the critical element will be lying at the topmost and bottommost. So I am taking the topmost point. So this will be the sigma b, and here also normal stress will be sigma b. And the next one is shear. Torsional shear will be acting in this direction. So this will be 20. So I can represent the element in straight here. So this will be the rectangular element. And here I can mark the bending stress sigma b. This is sigma b. Again the torsional shear stress which is acting like this. So this is 20. So if you are observing, this sigma b is actually the normal stress along sigma x direction, sigma x. And there is no normal stress along y direction, or sigma y component is 0. And this tau t is the torsional shear which is actually the produced. This I can represent as tau xy, which is actually the torsional shear produced due to the torque applied. And one point to note is that earlier in these equations I have used the property sigma yield as sigma y. I have represented yield as sigma y, that is actually the property. But here in the two-dimensional state of stress also I am using sigma y. I could have used some other thing, but you should understand what it is. It is actually the stress component along the y direction. Here sigma y, the stress along y direction is 0, but actually there is yield strength is given in the problem. So in this equation that sigma y is different. So anyway this component is 0. So based on these values, I will be evaluating the principal stresses. For that, I need to simplify for these components, that is sigma b and sigma tau xy or tau t. So understand, Here sigma x value is equal to, due to bending, sigma b, which is 30 to m by pi d cube, and sigma y value is 0, and the tau xy value is equal to the torsional shear tau t, and which is equal to 16t by pi d cube. So based on this one, I will be finding the stress components here. So first I can calculate the sigma b, which is 32 m by pi d cubes. 32 into bending moment is given in the problem, which is 3500 Newton meter divided by pi d cube. D is the unknown, so I can keep d cube in the denominator. Then we will be getting a value of 35,669 divided by d cube. Similarly, I can evaluate the tau t, which is equal to 16 into torque is 2500 Newton meter divided by pi d cube. Then that value will be getting as 12,732 divided by d cube. So this is actually the sigma x, and this is actually our tau xy, and we know that sigma y, or the normal stress along the y direction, is 0. This is no, please note that this is actually not the yield strength. We will be using the same notation later for applying the failure theory. So from these equations, or from these components, I can evaluate the principal stresses sigma 1, 2. Sigma 1 will be the maximum principal stress, and sigma 2 will be the minimum principal stress, based on the expression sigma x plus sigma y by 2 plus or minus. If I am substituting plus, we will be getting sigma 1. Otherwise, sigma 2 minimum principal stress, you will be getting sigma x minus sigma y by 2 the whole square. This equation I have shown in the data book in earlier videos, plus tau xy square. So here this value is 0 and this value is 0. So you can substitute sigma x is equal to this one, 35,669, and tau xy is equal to this term, 12,732 by d cube. So if you are substituting the plus 1, then you will be getting the expression for sigma 1, which is 39,747.3 divided by d cube will be getting, and the minimum principal stress sigma 2 will be getting as minus 4,078.3 divided by d cube you will be getting. You can try yourself and verify these values. So this is the maximum principal stress and minimum principal stress. This is the first step in solving problems from failure theories, or specifically static failure theories. So once you are evaluating the principal stresses sigma 1 and sigma 2, you can apply the static failure theories. Here we will be solving the failure theories one by one and evaluate the value of this D, the diameter of the shaft. So we know that our first theory is maximum principal stress theory, or Rankine's theory. So according to this theory, we are actually comparing the principal stress sigma 1 with respect to the yield strength. Here factor of safety is also given, so I will be considering this one. This is the equation I have given earlier. So here sigma 1 value is we have evaluated, which is 39,747.3 divided by d cube. In limiting condition, I can put equal sign. And yield strength is given in the question, which is 231 megapascal, or 231 into 10 raised to 6 SI units. I will substitute, divided by factor of safety. We have to take a value of 2. It is also mentioned here. I can solve for D, so I will be making use of the calculator. So some part of the calculator is visible. Anyway, this display page you can see here. So here d cube will be equal to 2. This d cube will be equal to 2 times this 39. So 2 into 39,747.3 divided by 231 into 10 raised to 6 value will be getting, and that is d cube. So you need to find the value of cube root. So the answer raised to 1 by 3 I can evaluate. Then you will be getting a value of 0.07007 SI unit. It is meter, which is equivalent to 70.07 mm diameter for the shaft according to the first theory, that is maximum principal stress theory. So next we will be applying the maximum shear stress theory. So this is the answer for the first theory of failure. So next theory is maximum shear stress theory, or Gust-Truscott theory. So here we are having the equation sigma 1 minus sigma 2 lesser than or equal to sigma yield divided by factor of safety. So I will be applying the values of sigma 1 and sigma 2. Here it is 39,747.3 divided by dq, minus of sigma 2 value is actually 4078.3 divided by dq and equal to 231 into 10 raised to 6 by factor of safety is 2. Here again this minus of, actually it is also minus, so minus will be coming as plus. So here I can find the value of d cube. So first I will be solving here. So 39,747.3 plus 4078.3 into 2 factor of safety divided by 231 into 10 raised to 6 and raised to 1 by 3. This above value is d cube, so I can find 1 by 3. Then you will be getting a value of d equal to 0.07239, which is equivalent to 72.39 mm. So earlier we have obtained a value of 70 point something mm. Here it is 72.39 mm. So this is the value according to the second theory, maximum shear stress theory. Next we will be applying the third theory, which is maximum principal strain theory. The equation I have shown in the data book, or Sein-Vanens theory. So here the equation is similar to earlier case. It was sigma 1 minus sigma 2. This will be sigma 1 minus mu sigma 2, where mu is the Poisson ratio. Again this is lesser than or equal to the property sigma yield by factor of safety. Here material is ductile, so I will be applying the yield one. And here I can substitute the values 39,747.3 divided by d cube, minus of mu is 0.3 into sigma 2. Sigma 2 value is 4 minus 4078.3 divided by d cube, lesser than. In limiting case I can apply 231 to 10 raised to 6 by 2. So again this one also I can solve using calculator, and we can find the value of d. If you are solving this value, then you will be getting around 70.79 mm. So this is the one according to the third theory, that is the maximum principal strain theory. Similarly, we can find the values of diameters for the next two theories. The fourth theory is maximum strain energy theory. Maximum strain energy theory, or it is also known as Haigh's theory. So I have shown you the expression. This is sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 lesser than or equal to property sigma yield by factor of safety. Again this values you can substitute. Sigma 1 is 39,747.3 by d cube the whole square plus minus 4078.3 by d cube the whole square minus of 2 into mu Poisson ratio is given as 0.3 into these values 39,000 something divided by d cube into the next value, that is minus, and that minus and the minus will be coming as plus, which is 4078.3 divided by d cube and the whole square, which can be equated to the 231 into 10 raised to 6 yield strength by factor of safety. Once you are solving this correctly, then you will be getting a value of diameter equal to 70.89 mm according to this one. In a similar way, we can solve for the last one, which is the maximum distortion energy theory. Distortion energy theory, or it is also known as von Mises theory. So here the equation is sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. Instead of 2 mu sigma 1 sigma 2, it is minus sigma 1 sigma 2, and this is can be equated to sigma yield by factor of safety in a similar way that I have shown earlier. Here also you can find the value of diameter d, then you will be getting a value of 71.34 mm. So all the values are in the range of 70 or 71, 72 around. So this is the way how you have to solve a problem from the theories of failure. Here it is maximum distortion energy theory. Earlier I have solved with the strain energy theory 70.89 mm, and this is principal strain around 70.79. This is maximum shear stress. Here we have got the maximum value 72.39, and the other one, this was the first theory, maximum principal stress theory. So this is the way to solve the problem. First we need to evaluate the principal stresses, then we just need to apply the failure theories. So that's all for this one.